All right. This is Physics 4A. This is the exam we had yesterday, but I'm also giving, and I'm taping the solutions, and I'm also sending to the 2A students. So some of these problems are not good for 2A, and I will let you know which problems are. Some of the problems are both for 4A and 2A students. So let's see how they go. I will not do all the detailed calculation. I'm assuming you can do that. So here you have three forces, right? F1, F2, F3, F1, F2, F3, and these three forces lie on an inclined plane. And so the net force allows this block to move up zero point 0.6 meters along the slope. And your job is to find the work done by each one of these forces. So the work done by force F1 is the magnitude of the force times the magnitude of the displacement times cosine of the angle between those two vectors. So magnitude of force 1 is given, and it is 20. The magnitude of displacement is given, it's 0.6. Cosine of the angle between F1 and the displacement, right? So the displacement is pretty much this, cosine of 0. And this is 1. So then you got yourself 12, 12 joules. Now, the work done by force number 2 is going to be the same equation, 40 times displacement times cosine of the angle between those two, and the angle is 30. And the work done by the force 3 is 0 because we have a right angle there. That's it. Second is a problem that requires um, first of all, you need to read the problem, and second, to find out what the problem is asking. And I'm kind of done correcting this problem, and I would say 80% of the students, or if not more, they try to determine the energy of the system. Because I don't know, I think students saw the spring and they thought they should, use half k x squared. But you should read the problem first and try to understand what's being asked, and then go step by step, and find a solution. So let's read the problem. So we have two identical massless springs, and the unstretched relaxed length is 0.25. So you have springs that are relaxed, so the size of each one of them 0.25 meters, and the K is given. It's a given quantity, newtons per meter. The springs are attached to a small cube and stretched to a length. So now they're going to be stretched. So it's not going to be like this, but more like that, right? And this is the original length. This is the original length. And they are stretched to a length of 0.3 meters. So they're going to be stretched to an additional 5 centimeters. Okay, both um, both springs. So essentially, if you look at this diagram here, L is basically 0.25 plus 0.05. So L is 0.25 plus 0.05, correct? So that's how we start the problem. So if you were to do a free body diagram here, you'd have your weight, you'd have your normal force. This spring would be attempted to bring the cube to the right, and this spring on the left would attempt to bring the cube to the left, and these two forces would cancel out. And in fact, if you just wanna start out your thought, each of these forces, let me call this force spring, each of these forces would be equal to this quantity K times how much of each of the springs have been stretched. Right? So that's the magnitude of both forces, and they cancel out whatever newtons. Now you go to a situation, look what happened now. An external force pulls the cube at a distance 0.02 meters to the right and holds it there, right? So then you have another figure here. So now what happened? You have the original size of the spring plus this much plus an additional 0.02 or 2 centimeters to the right, and this other spring now is 0.25 plus 0.05, that's original length, remember? But it has been compressed, not compressed, has been pulled to the right by that much. So here is how much of the spring is now stretched. It's 0.03. And this indicates how much of the left-hand side spring has been stretched now. So it's more stretched. So if you do a free body diagram, and that's what I wrote to some students, and then I stopped writing, you should start this problem just doing a free body diagram. You put your cube there, you have your force P, you have the force to the right, which is called F to the right, and you have F to the left, right? So the force to the left, which is exerted by this spring, is equal to the spring constant times how much of the spring was stretched. So this is negative to the left, plus the force P plus 700 kilograms newtons times how much of the spring was being stretched, 0.03, and the force is to the right. Okay. So when you and this net is zero because the system is in equilibrium, and then with that you can find P. See, because this is a number, this is a number, you can find P. P is a force. What is the force? Newton's law. It's a simple Newton's law thing. So this problem is good for 4A students, is not good for 4B, for, 2A students. We have a rock that is subjected to a variable force. Variable force. See, the force is variable, is distance dependent. So see, if a force is variable, you can still use Newton's second law of motion. What you cannot use is all these equations of motion. This equation of motion that we use a lot in chapter 2, you cannot use because your acceleration is not uniform. Is not uniform, which means it's not constant, because your force is not constant. It depends on position. And the acceleration is not constant either. So you cannot use this equation. So how do you solve this type of problem? You could use conservation of energy. And again, this problem is not for 2A students. So the simplest is to use the work kinetic energy theorem, and that says the total work of all forces on a given object equals the change in kinetic energy of that object, right? So, but what is the work done by this force as it moves the rock 9 meters? Well, the total work is the integral from 0 up to 9 meters of F dx. And that is equal to the change in kinetic energy, which is half mass times v squared. And we want to find the speed. So and then it's just a matter of integrating, right? So 6 minus 2x plus 6x squared, integral from 0 to 9 dx is equals 6x minus 2x squared over 2 plus 6x to the cube over 3 from 0 to 9. And then you can find what is going to be the work once you complete this equation here. And then since you know the mass, which is 7 kilograms, you can find the speed. And I think the solution was about 21 meters per second or so. The problem number 4 is a problem that I gave on a handout. I just found out. I gave in a handout or in a class sheet to the students. So there is a 2 grams bead along a frictionless wire, showing the figure. Point A, the bead is moving to the right. Negligible speed, it means the speed is equal 0 meters per second. Okay. So what is the potential energy of the bead at point A? So potential energy at point A, you have a general expression for it. If your ground level is given by this broken line, the gravitational potential energy is given by mgh, and that is equal to mass. Don't forget to take that in kilograms times 9.8 times 1 meter, 100 centimeters. This is equal to 1 meter, okay? And then you have that in joules. What is the kinetic energy of the bead at point B? Well, assume there is no friction. The total energy at this location equals the total energy at this location. So if you do your little table, right? If you do your little table, your energy tables, point A, point B, kinetic energy at point A is negligible, speed, so is 0. At point B, that will allow you to get the velocity at point B. Gravitational potential energy is given, that is what we calculated at part A. So whatever number you have here, you call this PGA. So you plug it right here, PGA, and at B is 0. So you add those numbers. So PGA, which we calculated previously, is equal half times 0.00, now I forgot, it's 2, 0.002 V squared, and then you can find your V. Oh, you don't want to find V, you want to find kinetic energy. So that's it. The kinetic energy at point B is the same potential energy at point A. So whatever number you have here, just repeat it in here. It's the same. What is the speed of B at point B? You can get it from this equation. And what is the speed of the bead at point C? So at point C, you repeat the same equation, right? The energy equation. So let's do that. So you can take, for instance, A and C, go down to your kinetic energy. At point A, I don't have kinetic energy. At point C, I have some kinetic energy. And we want to find the speed, so I would get the speed from here. How about gravitational potential energy? I do have an A, I already calculated. And at C, I also have gravitational potential energy, which is mg times the vertical displacement, is 0.8. And that's it. So you add this nonsense. I already subtracting. And then you can find your speed. Okay? So you add those two numbers, you get one equation in the right-hand side, an equation on the left-hand side, and then you play around, probably taking this quantity to the other side, change the sign, you know that math, right? The last one is number 5. You have a stunt car driver negotiates the frictionless, no friction, track, which is complicated. If there is no friction, how come the wheels can spin? Right? It cannot. Car would slide. Track down in such a way that the car is barely in contact with the track at the top of the loop. So when you get to the top of the loop, to say the car is barely in contact, what does it mean? It means that if you do a free body diagram right there on the top, right? Put the car in there, and then you bring about which forces are acting on the car. In general, you have the weight of the car at that point, and you also have the normal force. The normal force, which is the force the track exerts on the car. Now, if it's saying the car is barely in contact with the track, it means at that point your normal force is gone, is nada, is zip, it's pretty much gone. Which means if this is true, at that highest point, your gravity force is your sole centripetal force. Call this point C. Okay? And that is mg is equal half mvc squared. And then you can get your velocity at point C as being square root of 2 sorry, I'm kind of I'm doing a big boo-boo here. I'm doing a big boo-boo here. I'm messing up equations. Okay, let's do all over. Okay. So the gravity is your centripetal force. Centripetal force is mvc squared over r. Okay, I put an equation of kinetic energy. I apologize for that. Okay, so mg is equal mvc squared over r. M cancels out. And then your velocity is going to be square root of rg. Okay, that's better. Okay, so then you can find the velocity at point C. So you have the velocity there. So the velocity here is the square root of gr. Very good. So what you need to do is, in g we have and r we have, right? So what the problem wants us to do, find the magnitude of the force of the car on the track when the car is at point A. So if you take point A, there are forces acting on the car. So you have a gravity force that pulls the car down. In the vertical direction, you you have in the horizontal direction at point A, the only force that is exerted on the car that goes along this direction is the normal force. So here's your normal force, right, at point A. And the normal force in this case is your centripetal force. Is your centripetal force. Since, let's say, if it's frictionless, assume the car is sliding, those are the only two forces on the car. But the gravity does not do anything along the direction connecting the track to the center of rotation, only the normal force. So the normal force at point A, is your centripetal force, mva squared. Oh, I'm sorry, I did it again. Yeah, no, it's right. mva squared over r. Okay. So we want to find the magnitude of this force. So to find the magnitude of this force, we must find what? The velocity at point A. How can we find the velocity at point A? Well, we know the velocity at point B, and then we can use conservation of mechanical energy to figure things out. So you have point A in your semicircle, right? And you have point C at the top. Since there are no frictions dissipating mechanical energy in your system, you can do your little table, energy table, point A, point C. You go to your kinetic energy. At point A, kinetic energy is half mva squared. And again, just to remind us, to find the normal force, which I have to find what is VA. And at C, the kinetic energy is half mvc squared. And I do have VC, right? I do have VC. So that's so much for kinetic energy. For potential energy, I have mg 2 times r, right? 2 times r is the distance from the point C to the ground level. 1r, 2r. And on point C, I have mgr, right? At point C, I'm sorry, what am I doing? No, point A is mgr, so I'm mixing up things. And then point C is mg2r, mg2r, mg2r. Okay, and then I can find my velocity at point A. So half mva squared plus mgr is equal half mvc squared plus mg2r. M cancels out, does not depend on mass, and then I can find my VA because I have everything else. Okay, and this was pretty much our exam.